Good morning to one and all. Now we will discuss the probability of error using the signal constellation. The calculation of average probability error using the signal constellation. Now to understand the process, here we'll consider an observation space that is Z and partition it into the region that is Z is equals to Z1, Z2 up to Zm. That is based on the maximum likelihood rule, that is the decision rule. Now, to understand the probability of error, we go through a complete process of communication system. Here, we can see, now to understand the process of calculating the probability of error, we go through the process of communication system. Initially, the message source that is used to generate the M array output signal. After this, the vector transmitter encodes each symbol into signal vector SI vector having n dimensional where n is less than equals to m. Now we'll see at the transmitter side, the modulator converts vector sequence SI into sequence of finite energy signal SIT, that is compatible transmission via channel. So the M array is transmitted into SI, that is function of T. Here we can see during the transmission there is a noise that is called as your additive white Gaussian noise denoted by WT, that is your front end receiver noise. So at the receiver signal we get XT is equals to SIT plus WT. So after this the receiver signal XT is passed through a bank of correlator that is denoted by X vector. Now using the signal constellation in observation space Z having M decision region, called it as Zi, where I is equals to 1 to n. So now we see over here we represent the transmitted vector Si and receiver vector X vector. So the tip of Si is transmitted signal point while the tip of your X vector is the receiver signal point, and the difference between the coordinates of X vector and S vector represents the noise vector. So we'll take the first case. In first case, when your X vector lies inside the region Zi, then there is less possibility of error. While in the second case, when your X vector lies outside the region Zi, then there is possibility of error, which is called as your average probability of symbol, that is denoted by PE. Here the averaging error occur due to overall possible transmitted symbols. Now we'll see mathematically we represent PE is equals to summation L equals to summation L equals to 1 to m p mi sent, that is the probability of transmitted signal, into p X vector lies outside, that is Zi mi sent, where it is your conditional probability of X vector. Now we will assume that the all transmitted signal are equiprobable. So we can say that the m suffix I sent is equals to 1 upon m, where I is equals to 1 to capital M. So therefore we can say that P is equals to 1 upon m summation I L equals to 1 to n into probability of X vector lies outside Zi mi sent. Now we already know that the conditional probability PE is equals to 1 minus the probability. So 1 minus 1 upon m summation L equals to 1 to n into P X vector lies inside Z mi sent. Now we see that PC is equals to your P X vector that lies inside the Z suffix I and your mi transmitted signal sent. So we can say that the conditional probability PE is equals to 1 minus 1 upon m summation L equals to 1 to m into PC. So we can compute that the PC is an integration of conditional PDF over region Zi. So we can say that the probability density function, also called as your likelihood function. So we can represent it PC is equals to integrate Zi fx. This is your conditional probability density function. So the PC is equals to your conditional probability density function. Therefore your P is equals to 1 minus 1 upon m summation L equals to 1 to m integrate Zi into your conditional probability density function, that is also called as your likelihood function of received vector. So here we can say that we have a noise in the channel, that is your additive white Gaussian noise. So the computation becomes complex over here. So the region of integration is simplified and an approximation to the integral is obtained as an upper bound, that is called as, this process is called as your unibound of probability of error. Now coming on to the union bound on probability of error, we consider additive white Gaussian noise, which is the set of m equally likely transmitted signals are propagated. So here we can see that your x vector is equals to your si vector plus w vector, that is closer to the signal vector sk than to si vector, for I is equals to k is equals to 1 to m. Here we can say, through the figure we can say, this is a SI vector and this is a x vector. We want the sk vector and x vector to be close so that there is the less probability of error. So we can say in the region Zi, there is the difference between the x vector and sk vector help us to find the probability of error. So we call it as an event. So it is denoted by a suffix ik. Now we see that the conditional probability, that is your PC, where the symbol mi is transmitted to PEMI is equals to P AI1 union AI2 up to so on, that is less than is equals to summation k equals to 1 to m or k is not equals to I into P AIK. This condition should always less than or equals to the sum of probability of individual events. Or in other words, we can say that the probability of additive white Gaussian noise can be computed in terms of conditional symbol error, that is symbol mi is transmitted. So probability of mi is less than equals to summation k equals to 1 to m into probability of a suffix ik, where I is equals to 1 to m. So this is known as your, this is called as your union bound on probability of error when the symbol mi is transmitted. So this was all about the unibound probability of error. Thank you.